So first off, really good in putting in the definitions. That's going to become important. But then let's go through and take a look at your answer. So you'd say seawater is a compound because we can break it down into sodium chloride and have sodium and chloride by a chemical reaction. So I would completely agree that sodium chloride is a compound that you could break down into individual elements. So is seawater just sodium chloride?
No.
What happened to the water part of that statement? So if you look at seawater, yes, you have sodium chloride, but you also have water present. Okay, are sodium chloride and water chemically linked to each other in seawater? Or would you be able to physically separate them away from each other? If
No.
you can physically separate them, then they are not, it's not a compound because they are physically separatable. If they're chemically separatable, then that's where you have to move in and call them a compound. But in this particular case, we're not looking at this as a compound, or seawater isn't a compound because they are physically separated. You could boil the water off and be left with solid sodium chloride. Okay, so those are certainly not a compound. And so, yeah, your definition in compound is that chemical reaction. So element, is it a single element? Well, you've already addressed sodium chloride as two elements, so element doesn't make any sense. A heterogeneous mixture, definite composition, variable properties. So that definition, while may be true, isn't going to be particularly useful for you. What you might go back and do is reference when we talked about it in lecture, which I know was a hell of a long time ago. But the easiest way to differentiate our heterogeneous versus our homogeneous is that heterogeneous is multi-phase. Multi-phase. Whereas homogeneous is same phase. So if you were to look at a mixture of sand and water, you would see that there was multiple phases. You have the solid sand and the water all kind of swirled together. That would be a heterogeneous mixture because you see multiple phases. Same deal with oil and water. They're both liquids, but you can see those multiple phases. Okay, that makes them heterogeneous. And here lies the problem that I've got with this question. They aren't really saying seawater. What they're saying is salts dissolved in water. When you have salts dissolved in water, do you see multiple phases? If they're dissolved, no. So it's not a multi-phase system, which then means it's all in the same phase and we're looking at a homogeneous mixture. Anybody that's actually seen seawater, so if this question was asked in San Diego, I'm sure I'd get all sorts of different answers. Since we're in Arizona, some people may not have seen the ocean, depending on travel and finances and all that kind of fun stuff. But in San Diego, if we took a scoop full of seawater, we would very clearly be able to visibly see different things floating in it. And that's where this question runs into very dicey territory. And you have to be careful with how you interpret what the question is asking. So in this case, we aren't saying pull a bucket of water out of the ocean. We're saying if I take sodium chloride and other salts and I dissolve them in water, what do I have? Do I have a compound element, heterogeneous or homogeneous? The reason they're using seawater is to try and make it a more real-world application. The problem is the real world's a little bit messier than we're attempting to have you see. So, in this case, homogeneous makes the most sense for this answer. This format of question has always kind of bothered me, and perhaps it shouldn't. What they're assuming in here is that this percentage is the mass percentage. And that is very often implied through the question in some form or another. And it's sometimes that implication, I think the issue is that people find that implication to be obvious, and so it's not referenced. I don't think it's obvious, personally. So when we're looking at things that could be solids, mass typically makes sense. If we're looking at solutions, volume typically makes sense. So if you're looking at a percentage of alcohol in an alcoholic beverage, it's ABV, and it's alcohol by volume. So the phase largely dictates the percentage. What happens when you move up to a gas? Well, gases could go either direction, either mass or volume. In this case, since we're looking at a compound, it doesn't make sense to refer to platinum in that compound by volume, because it isn't occupying a volume, it's occupying with the rest of the atoms that whole space. So mass, again, is going to make the most sense here. So if we want a percent by mass of platinum, well, percent is by definition a deviation or a division here. Since we're saying it's mass, we're looking at the grams of platinum. But the grams of platinum where? Well, the grams of platinum in the mass of the compound. Okay, so where could we find information about the mass of platinum?
On the periodic table.
Yeah, the periodic table tells us for one, and I can't look at it right now. I can adjust. Tells us that the mass of platinum, depending on which unit we want to use, would be 195 grams of platinum per 1 mole of platinum. Okay, and this unit thing is going to become a big mess here in a second, so what we'll do is just kind of ultimately simplify it. If I have 1 mole of platinum, how many moles of the compound do I have? Well, it's going to be 1. That's the relationship that comes out of that formula, which ultimately means this whole mole thing simplifies out, and really all I need to do is say that the mass of platinum is 195. Okay, 0.08. Okay, and the unit on that isn't a big deal as long as I use the same unit for the mass of the compound. So I could use grams, I could use AMUs, I could invent a unit. As long as I'm maintaining this number relationship, it's fine. Okay, so grams tends to be the easiest one. So now what would be the mass of the compound that had this platinum? Well, where would I find out about the mass of the compound? Well, what's in the compound? Well, I have xenon, I have platinum, and I have fluorine. Well, what's the mass of xenon in that compound? Again, periodic table, 131.29. The platinum we just looked up was 195.08. The fluorine comes in at 19.00, but there's 6 of them, so I'd have to multiply that by 6. And now all I have to do is add all those numbers together. And I conveniently don't have a calculator handy. I'll just use my phone.
440 and 37.
Okay, I'll just trust you. 440.37. We can now put that in here, 0.37 grams of compound. So I'm just going to write CPD. And now I just do that division. 195.08 divided by 440. And you said 37 and I wrote 39 because that was convenient. Okay. If we come through and get a final answer on this, my calculator's at least telling, and then I always forget to say this, you also need to multiply by 100 to get a percent right again. So if we do that, we should get 44.2999. 2 nines. Okay. Sig figs, we should be approaching this and addressing the sig figs appropriately. Though this question, ultimately, it's irrelevant because every single one of your answers has been provided to 3 sig figs, which means you should provide your answer to 3 sig figs. 442 The first insignificant digit is larger than 5, so add 1. And you would get 440 or 44.3, which is, where did it go? C. And you have C as that final answer. Kind of makes sense?
Yeah. So then if you can jump to 63, it's a lot this.
Oh, if I wrote it, just in case, I'll write it here. So the percentage of water in borax, this one's a little bit more complicated because you have to do a larger interpretation with the formula, but it's the same process. So what are you being asked for? The percent H2O. Again, we should make the assumption we're looking at grams. So grams of water in what? The grams of our borax. So now we would have to go through and interpret how many or how much water was present in borax. In the previous example, we could just get away and say, well, platinum. And if we tried to go through and do that here, H2O, 2 hydrogens times the mass of, if you really want to go sig figs, 1.01, 1 oxygen times the mass of 16, and we tried to add that up, we'd get 18.02, which is fine, but if we tried to interpret that and drop that into here, we now have a problem. Because that's not just the water that's in borax. This is where we have to look carefully at our formula, and when we look at the formula of this, there are 10 water molecules in borax. So this isn't just 18, this would be 18 times 10. The amount that I should be looking at would be 180.2. And that's how much should be showing up in the numerator. So 180.2 grams of H2O. The grams of borax, for going underneath, similar to as we did before, sodium 2 times 22.9. Boron, is it 4? 10.81. Oxygen, and this is where I would personally do it, I would say 7 times our 16.00. I'd get whatever that number is. Calculators, 2 times 23 plus. And I'm not convinced that my cell phone does orders of operation right. It's approximately 202. I have to combine both the water and that together to get the correct amount of borax because 382, the water was part of borax. So in this case, it looks like somewhere near 50%, so D. So yeah, this question really is just leveling in, do you understand all of the information embedded within a formula? But you're still going through the same actions of your percentages. Okay? Question. So this kind of notation is what is known as a hydrate, which we didn't really address in lecture because I personally find it to be kind of a minuscule aspect of information, and I mean, it's not, yeah, we don't need to get into my opinions on it. It is addressed in the lab, and so what that dot is referencing is that those pieces, okay, or the halves, if we look at this, there's 2 halves, we'll call it the red half and the blue half, are inextricably linked. Okay. But they're linked in such a way where they maintain some of their chemical identity. So if we were to rewrite this formula as, let's see if I can pull this off, Na2B4O17H20, what we've now done is, while it's still representing technically the same compound or the same elements that are present, what it has done is it has removed the information that the hydrogen is bonded to oxygen in a water molecule, and that those water molecules are now in a larger crystal structure. Okay, the hydrate is just trying to emphasize that we have separate identities in the thing. It's kind of like an ionic compound. We have sodium and chlorine. When they come together, they make table salt. Okay? If we just say table salt, we aren't referencing where they came from, so we could say sodium chloride to reference where they came from. They're independent pieces. We don't invent a new name for it. The same kind of thing is happening here, except instead of it being atoms that are coming together to make these larger structures, it's molecules that are coming together to make these larger structures. And so they're still maintaining their molecular identity, but they're now contributing to a larger thing. You could look at it like Transformers or Power Rangers. If those references made any sense to you. If the Red Ranger and the Blue Ranger can do things independently, but they can combine their forces to make a larger Reptizord to fight on larger bad guys. So that they can build on each other. They don't lose their identity. They're now kind of combined. And that's what that dot is kind of trying to reference. So let's address your very first question, which was you get confused with temperature and pressure and which things go with which and all this. So the first thing I would say would be, we talked about solids very early on in the semester. Did we address the concept of pressure when we talked about solids? No. We also didn't talk about pressure when we talked about liquids. Pressure only came in as a concept when we looked at gases. Okay? That's when we have a pressure appear. So if you are referencing the properties of a gas, pressure is something that should be considered. If you're not referencing a gas in any way, shape, or form, you don't need to worry about pressure. So, for instance, dissolving a solid into a liquid, pressure isn't really relevant, and it can largely be ignored. Okay? But if I'm going to take a gas and try and turn it into a liquid, pressure is now going to be important, because what I'm concerned about is how do I manipulate and understand that gas? Well, pressure is a property of the gas, and now it has to come into play. The pressure of solids and liquids is not relevant under most of our physical processes. Okay? Which is one direction that this question isn't directly asking, but you have seen questions like that in the past, and you might very well see them on the final. So, yeast and sugar added champagne to give the sparkle of carbonation. So this is again them trying to provide the real world application, which is an interesting one because they're referencing champagne, which for a class with an average age that's probably lower than 21, not the greatest or easiest reference. But we're assuming people have seen this or understood something about champagne. And that's why they follow it up with a statement. What are the conditions in which carbon dioxide gas is the greatest? Okay. Partly what they're assuming here is that you understand that the majority of champagne is water. So we are looking at how I get CO2 as a gas to become CO2. CO2 aqueous, okay, or dissolved in water. Okay. And to contrast with this, I also want to throw in sodium chloride as a solid and trying to get it to become sodium chloride aqueous. Same process, dissolved in water. And we want to kind of think about what's happening within these. So, solid goes to a liquid, goes to a gas. What do I need to do to get a solid to turn into a liquid?
Solid turn into a liquid.
Really simply, what do you need? Make a solid go to a liquid, or a liquid go to a gas. What do you need to do? How do I make solid water go to liquid water? I add heat. Okay, so I have to add heat to get those things to happen. How do I go from gas to liquid or liquid to solid? Well, I have to remove that heat. I have to cool it down. Okay, so let's take a look at what I would argue is the easier one, our solid one. If I'm going to try and take solid salt and turn it into aqueous salt, okay, you'll notice that that is now referencing a phase that isn't on this little list that we've drawn out here. But which phase most mimics the aqueous solution? Solid, liquid, or gas?
Liquid.
Yep. Okay, or most approximates. Okay, so if I'm going to take a solid and I want to turn it into aqueous, well, it's effectively saying I want to take a solid and turn it into a liquid. What do I have to do? Well, taking a solid and turning it into a liquid, I have to add heat. Okay, so increase the temperature. Okay, or go at high temperatures. That's going to facilitate that. Do I need to do anything with the pressure? Well, I'm referencing a liquid and a solid. Pressure's only relevant when I'm looking at gases. Since in this particular case of solid, of the sodium chloride, I'm not looking at a gas, I don't care. I don't care about the pressure. It's really irrelevant to the overall expression. What happens when I go up to CO2? Well, I'm now taking CO2 and trying to dissolve it. Well, we're mimicking again kind of the system that we're evaluating. Okay, and consider what's happening within that black box. When we looked at the salt, we went from solid to liquid. Okay, this was our sodium chloride. When we're looking at CO2, what's happening? We're going from the gas and we're trying to make it look liquid. Okay, well, what should happen to the temperature to make a gas look like a liquid?
Go down.
It should go down. So it needs to get colder. Okay. The next one that becomes harder is dealing with pressure. Because we do have a gas here, we have to address pressure. Okay. Gas and pressure have to be related to each other. That's when we discuss them, so we need to think about what has to happen here. Okay. So pressure is the amount of kind of pushing on the outside walls. And we don't really evaluate it with liquids because the liquid is always pushing on the outside walls. So there really isn't a change in the pressure. The gas, however, is only pushing on the outside walls when it hits the wall. Otherwise, it's moving freely in between and we don't see anything. Okay? The liquid will always be pushing on the walls because it's forced into that state. So if we're considering the pressure, do I want a large pressure or a small pressure? Okay? That pressure, if you can flip the concept, is the walls pushing on the particles. Okay? If there's a small amount of pressure, well, then the particles are free flowing everywhere in between, and we're now not looking like a liquid. The particle can move wherever it wants. Well, liquids don't move wherever they want. They only move to the bottom. Think of forces of gravity of your container. So if I want that gas to mimic a liquid, I need to force the gas to stop moving and to act like a liquid. To do that, I have to put immense pressures behind it. So pressure now becomes important because we're looking at a gas and I'm trying to force it to stop moving, which means I have to increase the pressure. If I don't want it, or if I don't care about motion, I'll open it up and now the pressure can move wherever it wants. Now we aren't going to get a liquid because each of those gas particles is going to move away from each other. The whole point of a liquid is that they're next to each other. So I didn't explicitly answer the question, but do you think you got it?
Yeah.
So when we're talking about chemical versus physical property, I find this one to be a bit odd. Physical properties, I think, make a significant amount of sense. There's a lot of kind of physical properties. Chemical properties are a little bit weird. A physical property is inherent to that individual substance, so it makes it a little bit easier to reference. A chemical property is now how does that substance react with another substance. So referencing chemical properties doesn't make a whole lot of sense to me. What makes a lot more sense would be chemical changes. And so properties themselves are a bit odd and not easy to list out in a particular question. And there's really only one place, or technically two words, that you could use to reference a chemical property in a multiple choice answer. One of them would be reactivity, which is by definition how it interacts with another particle or another chemical. Okay, so this is an interaction, or in particular a reaction, with another substance, which is kind of the tenet of a chemical property. It's how it interacts with other particles. So that's why that term comes out. So we'll say element, but it can be compound. The other word that can get used is flammability. Okay, and flammability I find kind of a bit misleading, or not necessarily misleading, but it seems to be very physical, because you go, oh, does it burn? And the issue is that I think there's kind of a cognitive block there. Burning is technically a reaction with oxygen. And because that reaction with oxygen is so incredibly common, because there's oxygen everywhere, and it's a very reactive species, that we invented a new term for reactivity specific to the reaction with oxygen. That's flammability. There are and so few that I can't think of any other terms that we could use that would encapsulate a chemical property that isn't reactivity as a term. So there's really only two ways that I can see this question being asked, is flammability or reactivity to get a chemical property. And then virtually, if not everything else, is a physical property. Because you aren't changing the bonds. And that's what defines a chemical, is the chemical bonds that connect them. So if you aren't changing those chemical bonds, then it's not a chemical property, it's a physical property. So yeah, I think it's kind of a dumb question in that respect. I think a better way to phrase it is to go off of the changes and say which of the following is an example of a chemical change, because now you can get a lot more specific and you can reference things and get a better concept knowledge down than referencing chemical properties. And so those chemical changes were change in phase, which there are multiple, but typically the reference there is formation of gas or solids, because those are the easy ones to see. Change in color and change in energy. And the reason why I like referencing these for chemical properties is that there is a physical change that also mimics each of these things. So trying to distinguish those, I think, becomes a more interesting and challenging question than just what is a chemical property and have you read enough to know what the words mean, as opposed to acknowledging something about the content behind it. Not sure what else to add on that.
So if there was like...
So malleability is the ability to deform when hit without destruction. So if you say hit a rock, it would shatter, and or that would be an example of brittle. That wasn't me.
Is that loud?
Yeah, it was kind of loud, but that's okay.
Oh.
I was just ironic that happened with the shatter.
Yeah, that's true too, actually. And that would be kind of a characteristic of non-metals. Metals, on the other hand, if you think of like gold or silver or copper, when you hit them, they don't shatter, they bend. So if you think about malleability, it's more of kind of a bendability. If they're bendy.
If something's malleable, is it able to, like, I know we've, like, hit this, like, beginning of the semester, but if it's malleable, it's, like, soft. Like, it, not
Yeah.
soft, but, like, you can change the shape of it.
You can change the shape easily. Yeah. Yeah, I don't know how else to describe it other than that, but I think that works. Think of jewelry. Specific gravity is just another term for density. So for an individual volume of that material, how much does it weigh? What would its mass be? So it's the mass to volume relationship. And that is a physical property because you aren't looking at other materials. It's that same material. What is its mass in its volume? That's your specific gravity. So when we're looking at the periodic table, these are kind of our rows all the way down. 1, 2, 3, 4, 5, 6, 7. And those are the hardcore kind of energy levels, and those typically refer to, and not even typically, do refer to the core electrons, if you will, so our S and P type orbitals. The problem with nickel as an element is that it's filling D type orbitals, not those core elements or those core electrons. And so the pattern of the 1, 2, 3, 4 for referencing the energy level doesn't quite work, and we start getting weird kind of offsets and fill patterns. So I understand why you're saying the third row. It's not the third row. It's in the fourth row, but the d orbitals are offset by 1.
Because
of the fill pattern and symmetry and other stuff that's probably beyond the scope of the class. So you don't need to know necessarily the why. You just need to know that it is offset and that your d orbitals start as 3d, even though they're in the fourth row.
Is that only for D?
It's also for F, which is less important for you because you'll never see that. Except the F gets offset twice because it's offset once because of the d orbitals, and then it's offset again for the same reason the d orbitals were offset. The F orbital's offset. So F comes in at 4F, even though they're in the 6th row.
Makes sense. Doesn't make sense.
And depending on what you look at and how you recognize the energy levels, and this is why in class I drew out all those kind of energy levels where then those things subdivided out, all that kind of fun stuff that everybody seemed to universally hate. That shows kind of the organization, why we would kind of move through things the way we do, and it allows us to understand that a little bit better. But we don't see images of that very often. In fact, the reason I have to draw it is because you don't see any images of that at all. I don't think it even shows up in our textbook. That people kind of zero that out and kind of ignore it and instead look at the periodic table and just kind of memorize patterns out of the periodic table. Which isn't necessarily wrong. I just want to make sure that if you're going to say third row, somebody looking at this knows why you're calling that the third row. And in the explanation, I didn't really see that. And so that's why I said no.
Oh, I see. So because
is that when you move to the left, the radius gets smaller. So what they're saying is the smallest is in this corner. Okay, which is true. The radius decreases from bottom to top. And it increases from right to left. Okay, so the trend that I think you just said that you added in there, this looks, I'm not going to say perfectly wrong, but I think close to that. to kind of look at the logic behind this, when we're referencing radius, we've got our nucleus, and then we have the radius for our atom. That radius is referring to this distance, the distance between the outermost electron and the nucleus. So the thing that's going to drive the size or the radius of your atom the most is your electrons. Okay? And so where those electrons are found. Well, where are electrons found? Electrons are in orbitals. And the orbitals are dictated based off of energy levels. So the first thing that we could go through and do is see where the energy levels change. When you go through your periodic table, okay, and for me it's easier to go down, as we go down the periodic table, what happens to the energy level? The energy level gets larger. Well, if the energy level is getting larger, that means your radius is getting bigger. Your electrons are getting placed further and further and further from the nucleus. So down a column, it's getting bigger. Okay, if you go up the column, it's getting smaller because you're getting placed closer and closer to the nucleus. Left to right becomes a little bit trickier because when we're looking left to right, we aren't moving through the energy level. We're staying in the exact same energy level. So when it comes to, say, organic chemistry, the change left to right is so minuscule we ignore it. Okay, and we ignore the change in radius in a row. We aren't in OChem, so what we have to do is actually address it here. What is changing as we move left to right? Well, it's not the energy level anymore. Our electrons are going into the same energy level. Well, if I place another electron in that same energy level, the radius shouldn't change because it's getting placed at the exact same location. And that's where OChem comes in. But the other thing that we have to address across a row is that the nucleus gets stronger. And that stronger nucleus means that we have more positive charge, which means that electron sees a larger positive in the middle and gets attracted in a little bit tighter. Which means when we move left to right on our periodic table, okay, we're increasing the amount of nuclear charge and we're placing the electrons at the same energy level. The net result is that those both contribute to the radius getting smaller left to right. Right to left, you're now inverting it, and they would now get bigger because you have less nuclear charge, still the same energy level. So it's recognizing nuclear charge and energy level as contributing factors to your radius. This is one that I would argue you should have your periodic table. You could even use the slides that I've got where I've got the trends written out and have that handy so that when you see a question like this, you're done. You've got the answer and you can move on. Okay, and there isn't a pause in, well, what was the trend? You have the trend literally right next to you when you're taking the exam.